So in the last lecture, I started discussing ion trap quantum computing, and what I described was essentially the structure of the trap, which arranges the ions essentially in a linear chain. And now I will discuss how the quantum operations are implemented on that linear chain. So just to repeat, this is a so-called Paul trap, which is time-dependent RF field in XY plane, and it is complemented by a weak harmonic and static, or rather it's electrostatic trap with some frequency which is omega z, and this RF frequency, let me just call it omega. So this is a structure. It's something you can design with Laplace's equation, and leading order description is all parabola. So it's around the minimum, and the curvatures are different in xy plane and in z plane. The z plane is static. This one has to continuously rotate, otherwise the ions will disappear. The saddle point solution in the static approximation. So this is one part of the story. Then the other ingredient which is used, these are all leading order terms, and that is all we are going to use. So the interaction of the electromagnetic field with the ion, and it's this Jaynes-Cummings Hamiltonian, and I will only write the interaction part, which is to be consistent in the notation for the frequency. So this is whatever the transition frequency is times A dagger sigma minus plus A times sigma plus. A dagger and A are the creation and annihilation operator for the photon or phonon. They behave the same way. And this sigma minus and sigma plus are lowering and raising operators for the qubit. And this Hamiltonian can also be used to describe the spontaneous decays of the excited state. Because what happens in spontaneous decay is this same kind of structure, the lowering operator on the atomic state and creation operator, the phonon. These are the same thing. So depending on the strength, you can use it, but the strength is already given by some frequency here, the transition frequency, and so there is nothing else left arbitrary, and the spontaneous decay is interaction with vacuum. You don't need anything else. Okay, so you can actually use it to estimate how stable your states are going to be. Because spontaneous decay is a process which is, in some sense, not an environmental disturbance because it just couples to the vacuum. But you can say the vacuum has quantum fluctuations, and that is what this is going to do, and you can never eliminate that. The other thing, you can do all kind of shielding, etc., and control, but this one won't go away. And that is something worth remembering. How does the rate which comes from this looks like? Okay. And there is a very straightforward calculation. So what is discussed in case of ions is dipole decay rate, because actually it is the electric charge which moves from one orbit to another, and the moving of the charge is a change in the value of the dipole. So dominant decay rate for most processes is actually electromagnetic dipole decay rate, and there are some matrix elements which come in, but the important thing is to remember the frequency dependence. And it goes like whatever the transition frequency is to the third power. Okay. And it has a generalization. So to arbitrary multiple transitions, there are selection rules essentially between the two levels. What is the change in the angular momentum, and that angular momentum will be carried over by the photon. And this dipole is L equal to 1, but in general it corresponds to omega raised to 2L plus 1. And so if you make states where the spontaneous decays which can only occur through large change in angular momentum, they are very stable. Okay, these are just quantum mechanical selection rules. But most of the time we just deal with the transitions which are going to be related by excitation or de-excitation by one photon, and this numbers comes in, and which makes that if you want to make the states long-lived, you must suppress omega. There is no choice. Okay. So you want matchable states, you must have the transition energy small. And the transition energies which we find in the, say, studying solutions like hydrogen atom, they are actually too large. They decay in a time scale of the order of nanosecond. We don't want that. And for that reason, in most of these processes which are used for quantum computation, the transition energy is in the microwave range. That is where you cut down this omega and cut down the spontaneous decay rate. You never use direct atomic levels of hydrogen that is going to decay too fast, whether you like it or not. You have to push it down to a microwave range. And the levels which are used in most of these cases are so-called hyperfine splittings of atoms. The hyperfine structure arises between the electron and the nucleus by dipole coupling. Its strength is quite well known in terms of many parameters. One well known phenomena connected with this hyperfine splitting is the what you call astronomical signal for hydrogen. It's known as the 21 centimeter line. Okay. So that 21 centimeter line is this microwave range, and it is actually the example of a hyperfine splitting, and those are the kind of energy gaps which you use for constructing the quantum bits. Otherwise, you don't get this stability with large time constant. So that is one thing to keep in mind. There is another thing which is also there, which restricts how long the states live, and that is not this a spontaneous decay, but what is known as a stimulated decay. So spontaneous decay is connected to vacuum. Stimulated decay needs a photon background. Where does it come from? Well, here again there is a universal feature, quite well known again in astronomy, the cosmic microwave background radiation, 3 degree Kelvin. That's the temperature. It's there. And it can induce decay, spontaneous decay. So this is and when you start talking about low temperatures, sometimes the 3 degree Kelvin is too high. Okay, we're talking about dilution refrigerator, it's much below that. You have to worry about it, what it will do. It cannot be expelled that easily. It's there, and you have to say that whatever I designed, the spontaneous decay from this is kept under control. And it needs estimates. So needed for whatever this H omega, whatever I can write the relevant parameter are these two. This is the thermal backbody radiation. And what is it going to do to your transition frequency? And you have to calculate it. Again, the stimulated decay expressions are all well known. The density of blackbody radiation is known. It's a universal feature. You need to plug in the numbers and calculate actually how fast this is going to happen. Okay. Okay. So these are the things, well, they're buried inside all the designs, and you literally have to make sure that your whatever device is stable enough to do quantum calculation. These things are so powerful that it's impossible to have a long-lived device beyond whatever few second lifetimes. Okay. And NMR actually can live longer, but there you are suppressing this transition frequency even smaller. It's actually the Zeeman splitting, which is much smaller than this hyperfine splitting, and so NMR state can live even longer. But all the atomic states are basically limited by all these features. So you have to keep track of them, and well, at least one should calculate and make sure that these things are staying within reasonable control. So now there are other requirements of this ion trap computing, which I mentioned, but I will sort of repeat it, that these ions vibrate in this direction. Because that one is a kind of weak potential given by this frequency omega z. This frequency is much tighter or larger in magnitude, so dominant motion is in the z direction, and you have to make sure that the this vibrational amplitude is much smaller than the photon. Wavelength, this is needed for addressing the individual ions. So ions are jiggling around, and the photon has certain wavelength. You have to make sure that whatever the jiggling is reasonably small compared to the photon wavelength. And this is a criterion which is used quite a lot. It is named as the Lamb decay region, and it is used in almost all experiments involving photons. If you want to address some objects, the photon wavelength has to be bigger than that, otherwise the coupling won't be uniform. You need a uniform coupling, at least for individual objects. And the other criterion was this double transitions are to be avoided. So we want to use this simple Hamiltonian. You have to make sure that multiple transitions don't happen at the same time. Okay. So yes, you are going to cause very perturbations by various kind of photons shining on the atoms, but you have to keep all this criterion in mind. And with all this background, I can now come to the actual protocols which are used to apply various kind of quantum gates on these atoms. And yeah, the what you call the 1-qubit gates are easy. They all work in the same way for all these various physical systems. Essentially, they are dictated by these transitions, and one direction is fixed, which is omega z, and these are in some sense in the transverse plane, where you can perform x and y rotations, just like as in case of NMR, no uh, difference. So these are transverse fields. They are all in the radio frequency range, and you use them with this Euler angle decomposition of rotations. There is not much difference of how these things are done, only the hardware changes, but the mathematical prescription is essentially identical. The important part is, which differs from various proposals from one to another, are these 2-qubit gates. And here now we have to think about how do you couple multiple ions which are sitting in different locations. So the coupling in these ion traps is through the center of mass oscillation mode, which has this frequency omega z. The whole register of ions actually oscillates together because it's the center of mass mode, and what we need for stability or yeah, the other way around. That you don't want to go into multiple phonon modes. So these are harmonic oscillator energy levels. The spacing is h cross omega, and if you don't want to go to higher levels, you have to keep the temperature so that the temperature doesn't excite it. So that is going back to this criteria. There is no double excitation. And typically, these systems work at millikelvin temperatures. So you need to go down in the temperature to satisfy that the phonons have a particular level spacing, and the level spacing are all decided by all these particular traps, and you need to go to low enough temperature to do the job. This does not require a dilution refrigerator because you are going to just put the ions in vacuum. And with a high vacuum, reaching such a low temperature is not a big problem. You can essentially cool down the atom to that particular level. So there are well-known techniques. By what is this called laser cooling. I will not go into details about it, but there are ways to cool down the ions to very low temperature. The same techniques as I mentioned last time is used for other low temperature systems like Bose-Einstein condensate or something like that. You can go down to high vacuum and low temperature, and the system has reasonable stability. Okay. So now, how do the transitions occur using the center of mass mode? For that means the ions have to couple their electronic energy level, which are this hyperfine level, and to the phonon level, which is also something which the atom can describe. So the system is described in a Hilbert space, which is one set is the hyperfine level, which I will just call ground state and excited state, and the other part is the phonon. So this is a qubit, and this is a phonon. The photon is there connecting this G and E. I'm not going to label it any differently. This is good enough to do that. But the phonon is something which is different set of states, and that can also make a transition. And this coupling is through the Raman effect. Okay. So, what did Raman discover? He discovered an effect which is present in essentially all molecules because the chemical bonds vibrate. So, you can talk about a single atom and its transition, that is completely okay, like in hydrogen atom. But when the atom is part of a molecule, what can happen is that when the transition takes place, the vibrational mode can also change. And when that occurs, part of the transition frequency can go to the vibrational mode or it can come back, both ways. And so, depending on the energy required for vibration, which is much smaller than the electronic separation of energy levels generically, what you find in molecular spectra is there is a big line corresponding to electron transition, and there are neighboring lines on both sides where one phonon is either created or it is absorbed simultaneously with the electronic transition. And those things are called sidebands. Okay. And both kind of what you call connections with phonons appear. It can be either emitted, the phonon, or it can be absorbed. And they are labeled as a red sideband on one side and blue sideband on the other side. Red is little less in terms of energy, blue is a little bit more. And that effect allows to couple these two spaces. Okay. So, in this scenario, exclusively red sidebands are used for this two-qubit gates. The system, okay, is designed so that after the operation you always come back to zero phonon state. But in between you can have excitations in the phonon case, and which will introduce some kind of a coupling. And red sideband means that the what you call omega for the whole transition is omega of the photon plus omega of the phonon. So, you always shine a light which has little less energy, and then it will combine with the phonon energy to actually make the transition. Or it can go vice versa. When the exciteds can decay, it can put part of the energy into phonon and part of the energy in the photon. So, going to be always what you call Hermitian operator, so it can act on both directions, either the phonon is created or annihilated. So now what is the strategy for the 2-qubit gates? Say that again, I cannot. Yeah. Center of mass oscillation modes means that all the ions are going to move together. It's a harmonic potential, but everything moves together. And the advantage of it is that you can use it to couple one atom to any other atom in this whole string in one shot. So the way the operation takes place is you do something over in one ion that will create a phonon. That phonon will propagate over the whole register, and you go to the other location, and there it will absorb the phonon. And it will, when the absorbing phonon, it will create some transition. And because when the center of mass mode is used, the distance between the two locations doesn't matter, because all of them are moving synchronously. And you emit a phonon in one place, absorb it at the other place, so that at the end you are in the ground state, and then these two ions end up getting coupled, depending on the operation you perform, which emitted the phonons or absorbed the phonons. Okay. Yeah, so the targeting is through having a light which can focus on individual ions. That I described last time, that the separation in this trap is about 30 micrometer, and the laser frequency is much below that. So when you shine a laser, you can focus it on one ion. And for the convenience thing, you don't move the laser whatever peripheral setup, because it's too complicated. You slide this ion trap back and forth, so that whichever ion want to address comes in the focus, and then you shine some light on it. Okay. So this there are three straps basically, which do the necessary operations. So the proposal, which was made first by Cirac and Zoller, it implements this control Z gates. In the description I will give soon. So why control Z? Because it's in some sense easy to implement gate. First of all, it is symmetric, so it has this matrix representation. It's fully symmetric between the two qubits. It's diagonal. Diagonal means that you can apply control Z in different locations. They all commute. You don't have to worry about it. And on top of that, you can also do, because all commuting operators you can apply simultaneously, etc., in different locations. That is also fine. So this has three steps, and they are written in terms of these pulses. So they are all Raman pulses. So pi pulse on ion A, then it's created by this sequence of operations. And you just have to work out the consequences of this one by one. The first, just let me give the details of what does a pi pulse on a single ion do. Okay. Now, pi pulse is something which takes the excited state to the ground state and vice versa. It's half the rotation. Okay. And transformation is basically just qubit. It's you can write it as sigma x as taking from ground state to excited state and vice versa, exponentiate it, and the duration will be decided that it takes you from one to the other or vice versa. So this pi pulse, what does it do? It will, well, actually you will do the reverse thing as well. Both are possible. So this operation is nothing but exponential of I sigma x pi by 2. The pi by 2 is because I call it pi pulse, but the spin is of that for a qubit, so operator is half sigma a. So you just have to write the cosine and sine of e raised to minus I times the Hamiltonian, and that is where this minus I comes from, the exponential of I times minus I times the Hamiltonian. Now, what does the red sideband do? That the ground state can go to the excited state only if that extra phonon energy is available. Otherwise, it falls short. So if this is 0, nothing is going to happen. But if the phonon energy is available, it can go to the excited state and the photon will get absorbed. The complement over here, when the excited state can decay, it will create the ground state, but it will emit one phonon simultaneously. So that is the effect of the red sideband. And now I can write down the result of these three operations. So better to write it as just a table, and I will omit this A and B just by a simple order, it's easy. And so I will start with the initial state in some order. There are 4 possibilities. And why it is all 0? Because I assume that at the end of or the beginning of you are always in the ground state of the phonon. Now we apply the first pulse, and it's going to act on the, this is A and this is B and this is phonon. Okay. So the ground state can go do something, but it needs a phonon. Phonon is not there. So nothing happens here, but something can happen here. So these two are unchanged, but this will get I, G, E 1 and minus I. This is again G, Now this is G still. So this is this pi pulse. Now I'm going to apply a 2 pi pulse, but 2 pi pulse is on the second ion. So what does a 2 pi pulse do? Well, it's going to complete a cycle. So the ground states and excited state labels are not going to change. But because I have a qubit, it is e raised to I pi times sigma, because the sigma by 2 is required for qubit. So the result is a change in sign coming from the sigma term. It's a qubit, and the 2 pi basically changes the wave function in sign if it is in the excited state. Okay, the polymetrics is still sitting there, so you have to take the convention. The ground state nothing happens, but excited state can flip in sign. So that will produce G on 1 will flip sign, and yeah. And it depends on the, well, yeah, which convention it is done. So e raised to minus I times sine pi. So no, it's a 2 pi rotation, so it will become sine of 2 pi, but there is a factors which are no converted. Wait, let me see. E raised to I 2 pi times sigma by 2. So e raised to I pi sigma. Yeah, it's the sign doesn't contribute. It's cosine of pi is minus 1. That is what produces the sign change. Okay, so this is going to occur, but it's only going to act on the excited state, which will flip the sign, and nothing will happen to the ground state. So this is the result, and then I have to apply another pi pulse over here, which will absorb the photons, not the photon, the phonon, nothing is going to happen in the red band anyway, but here the reverse operation is going to occur, which is the excited state. No, this one I already used. The ground state with one photon will come back to excited state, which is what it was originally, and the result is this E0, and there is something I missed in the signs depending on what I took. This last one is supposed to get a minus sign, and G and 1 gives a minus 1. So I think the convention is something like this. So minus I get squared, it becomes E, E and 0. The sign flip occurred on this ground state for the 2 pion, that is 2 pi pulse, and not on the excited state. Let me see the convention which is used. G and 1 will go to minus G and 1. Okay, so that is, this one is a 2 pi pulse. This is the effect of cosine of pi, whatever it is, it flips the sign of the state on the B side, and that is responsible, this minus I becoming plus I, but nothing happens to the state where it's an excited state, and there is a photon because there is not enough what you call energy available for the particular transition. It requires this, it's still in the red band, whatever it is. So this can occur, but this one is unaffected. It doesn't match in the frequencies. So the final result is all I and minus I and this minus 1 getting multiplied, is that the excited state, if both ions were initially in that state, it gets flipped in the sign, and the other ones don't, and that is essentially this control Z gate. So this is the scheme. It's a interplay of photon and phonon through all these Raman sidebands, but that is what is reasonably straightforward to implement, and it was demonstrated very early in this information processing business in the, I think, early 2000, that this 2-qubit gate in this particular scheme was demonstrated. It just well, particular Hamiltonian applied for a duration, but because we have a qubit which is a fermion, 2 pi rotation will flip the sign of the wave function, and 4 pi will actually bring it back. So that sign flip is essentially used to convert all this jugglery so that it becomes finally the control Z gate. Yeah. That has to do with this, all these whatever pulses are applied, they are all red sideband pulses. So unless this um, situation is satisfied, the ion will not respond. So it's very sharp frequency domains in which there is a response and the lines are sufficiently narrow. So the ground state will respond with one phonon, but excited state with one phonon doesn't have the same uh, dynamics to satisfy this Raman sideband condition, so nothing happens. This no, it acts only on this ground state. The it needs basically one phonon. So uh, you're asking why this doesn't undergo any transition. Well, it again the energies are tuned, so it will affect only state which has one phonon inside it and which has 0 phonons inside it doesn't do any transformation, but this is I think it is ruled out by some condition, and only the states which don't respond. Where this E0 because of the condition can become G and 1. That is possible in general, but something must be holding it back. Okay, I don't remember. I will have to look it up and tell you, but uh, this is the sort of proposal which was made, and it was verified as well as implementation of this control Z gate. And this was not the only possibility. People actually came up with some alternatives, and there is another two-qubit gate which is more common these days compared to this one, and it's known as a Molmer-Sorensen gate. It's not control Z, but it can be expressed with another 2-qubit transformation, which also is universal, just like Control Z made a universal logic gate together with 1-qubit rotation. You can use this 2-qubit gate also to make up a universal set, and that is encoded in a rather simple-minded approach, because it will mix the two states. So what it does is let me just write down I. There are factors of I which are there, and I just want to make sure that the signs are okay. So these two transform by just mixing with the factors of plus I, and the other two cases transform with a minus I. This is just the definition of this YY transformation. It is a tensor product of two sigma y matrices, and the duration is decided by this pi by 2. And what happens with the two tensor product is both are imaginary, both sigma y is imaginary. You have two of them become real, and this I comes from the e raised to minus I times Hamiltonian, etc. And the pi by 2 ensures that you mix them in equal proportion, because it's again a qubit. So the angles which appear in the trigonometric is cosine pi by 4 and sine pi by 4, which is this 1 by root 2 factor. And this opposite sign comes because when you act by sigma y, it's an off-diagonal matrix. G goes to E and E goes to G, but the sigma y is antisymmetric, so there is a sign flip if there are two opposite ones compared to the two which are the same type. Okay. So this is just a definition of sigma y a transformation, or rather this particular pulse. And the fact that it is a universal, that is fine. The question is, how can you implement it in the same ion trap structure? So it uses something a little bit trickier, not the same setting. So it uses what is known as a bichromatic light. What it means is a simultaneous use of red and blue. So you shine on these atoms two sideband pulses simultaneously. One of them is a red, the other one is blue. And there is no phonon. So So indirectly the phonons are there because both of them are in the sideband, but they are never going to appear as an excited state in the in between case. They will remain in a virtual fashion, and what is known as this detuning the of pulses is close to omega z. You still need to have these phonons as a kind of virtual in between states, which these are all tricks of quantum optics. But you can adjust the frequencies to be close to this or whatever the Raman pulse is for vibrational mode, and make sure that the single excitations are all suppressed and only double processes takes place. And when the double processes takes place, it will basically absorb one red quanta and one blue quanta on different ions and go from this state to this state, or vice versa. That has enough energy to go from basically G to E and E to G, or vice versa. And that is how this is done. It's a different strategy, but it can be implemented, and it has some advantage. And the advantage is that you don't have to worry about focusing on individual ions. You can actually apply this to the register simultaneously depending on what ions you want to address. It can be more global rather than much more specific, and that is why it is used. So allows if you apply this to a bigger domain, you will perform this operation which will untangle multiple ions in one shot. And that is one of the ways this gate is used instead of doing individual transformation on specific pairs. There are now various caveats or other sources of errors which people found out that what are the imperfections. So, one of them is a in this particular scheme, you don't have to necessarily cool all the ions to the ground state, because phonon is only used virtually, and not like going back to the zero phonon state at the end of it. If it is little bit imperfect, it doesn't matter much. That is another advantage of this Molmer-Sorensen gate. And the error which is, well, in this process turns out to be rather monodirectional thing, that one of the kind of error occurs far more often than the other situation, and this is the so-called phase error. There are many different kind of errors which occur between multiple qubits, but in this ion trap situations, the dominant source of error is actually change of phase of the relative states. Multiple components like this value of I may be little bit different. And where does this come from? One is these various traps which you made with certain frequency. The frequency may not be perfect, okay. And that is called anharmonicity, and the frequency is not perfect, the phases will be little bit off in terms of where the ions are at particular instance, and that is something which you land up with, and the other error is these ions are moving back and forth in the trap, and it will produce a what is this is a path dependence. That the motion may not be perfectly along one direction, there might be little bit time lag, or there might be this vibrational oscillation creating some path dependence, and the errors which are coming from there are also basically phase errors. So the main challenge of experimental implementation is to reduce this phase error as much as possible, and that people have been able to bring down to less than 1% empirically by tuning various things, and well, they are trying to push it down even more to make better systems. But that is roughly the whole story, and people have tried all kind of things that how much of these assumptions of the Jaynes-Cummings model are valid, whether you need to do complete cooling, whether you want to implement pulse little bit faster to cut down the time of operation, and some of those things are possible. It turns out that you don't have to literally go all the way down. You can use somewhat stronger fields and get away with it, and those are empirical questions, and they seem to be working. But the main point is that various time scales which are decided by the decay rates as well as stability criteria, which tell you how many operations you can perform. And those numbers are typically of the size of order 100. You can't perform too many operations before the state decays, and that remains the ultimate limiting power of this realization for performing quantum computing. So that is as much as I want to say about these ion traps. And the next topic, which is overlapping to a large extent with whatever goes on here, though it is a different kind of hardware, is what is known as neutral atom quantum computing. The only difference is that instead of having ions, now you have neutral atoms. But that gives certain advantages, and that is why a lot of efforts are invested in that as well. And the ideas of what are the states and what are the transitions, they are not going to change very much compared to what are the levels here. All the Jaynes-Cummings models, they are all identical, but the fundamental components are very different, and they have an advantage. And that advantage essentially comes from the fact that the individual components are neutral. And so perturbations from fluctuations in electromagnetic field don't do much. Okay. In the ions, this anharmonicity or a path dependence, which I kind of mentioned here, they come because the ions are moving through an electromagnetic field, and that induces certain phases. Here it's a neutral atom, and if the electromagnetic field is there, it's not going to do very much. So that is a important change. But then the question comes about how do I hold neutral atoms in a place? That requires altogether different techniques. The reason being the ions responded to the electromagnetic field, and then I could design a trap to keep them in one place. Here the neutral atoms don't respond to the external field that much, so you can't use electromagnetic field in the same manner to trap them. And fortunately, there was a technique available much before all these things came along, and that is known as optical tweezers. So I will describe that next time. And it turns out that this works quite well in all kind of techniques, but you need something more. You just don't need objects which sit in one place. You all need the various kind of transitions. And for that, having just a neutral atom is not enough, because transitions like that in a hydrogen atom are very fast, and they will not do the job for you, and you can't even couple them to each other very properly. And the whole industry started with realization of what are known as Rydberg atoms. And these Rydberg atoms are a particular set of states which can be prepared experimentally, and they are long-lived enough to survive, and they offer you different ways of control which can be used for implementing logic operation. So before I go on to all that, let me just describe what is a Rydberg atom. And this is basically a hydrogen like atom with a valence electron at large radial quantum number. And these are certainly possible. The question is whether you can make use of it, and then you can try to understand its physical properties. Okay. And because there is only one valence electron and it's going to be away from the nucleus because of large radial quantum number, you can essentially borrow all the results of a hydrogen atom, because the nucleus is shielded by all the non-valence electron. The charge is essentially 1 and the electron charge is minus, and all the formulae which you can find in hydrogen atom description, they just carry over without much problem. And so what are the numbers here? So n which are used is in the range of 50 to 100. Okay. There is a reason for it, and you can still select which n you want to go to by particular transition frequency. That we will come to later. But what are the properties? So let me just use what is the radius of such an atom. It goes as order n square. It's just the same formula which is there in the Bohr model of the atom, where radius goes as n square and energy goes as 1 over the radius. It's order 1 over n square. Of course, you take such a large n, that means the energy will be smaller by a factor of say 10 raised to 4 compared to what is there in the hydrogen atom, and that will again bring it down to the microwave kind of a range, which is where you want to go to prevent again the same kind of thing, spontaneous decays and other kind of instabilities. We'll come to that soon enough. I will write down those results. But the point is, this radius is very large. So the hydrogen atom, the radius is in angstrom. So you multiply by 10 raised to 4, it becomes micrometer. And those are the same ranges in which you play around with all kind of hardware design. So this is in a micrometer, and this is a milli electron volt. This large radius gives you various other features which come with that one of them is a dipole moment. It's just a nucleus and the electron at such a distance, the distance has become large by factor of 10 raised to 4. The dipole moment also becomes large by the same factor. Okay. So and together with that is a question of polarizability, and this is how much the atom will distort in presence of a external field, and this one has you need to work it out more carefully with all kind of responses, but it's even a larger number like n raised to 7. Now, what is the description of these atoms? It is something which you need to go back and look at the semi-classical quantization of the Bohr model, because in the Schrodinger equation you will get a particular radial quantum number and then together with the angular quantum number which goes all the way from 0 to n minus 1. So, there are lot of angular quantum number levels available, and the picture basically gets generated into a sort of classical language where the largest angular quantum number orbit is essentially circular, and it becomes kind of oblong with decreasing L. L can go all the way down to 0. So, then the circular orbit, and slowly you go down in a smaller and smaller, and then it will become like an ellipse and the nucleus will be at one corner. So, this is a description which comes out. It is just for explanation, but the point is that what you want is this large circular orbit where the electron is far away from the nucleus essentially all the time, and that comes with value of large L. Okay. Now, what are the peculiarities of those particular thing? That the decays or well, let me say what is the spacing between energy levels? Well, you have to essentially count difference between 1 over n square and 1 over n minus 1 square, the adjacent levels, whatever it is, and that goes like order 1 over n cube. So, there are lots of levels, all closely spaced, but fortunately the electromagnetic pulses which can distinguish these various levels. That much accuracy available. But then now we can ask the question, what are the decay rates? Okay. So, as I mentioned earlier, the dipole one goes as 1 over sorry, not this, whatever this delta E cube third power of the frequency, and for this, I use this notation. Yeah. Omega last time, omega was same as delta E, and it goes like 1 over n cube, and dipole means delta L equal to 1. So, that is the reason for choosing large L means that the transitions will be only between adjacent levels. So, that is a selection rule from quantum mechanics. If you want to jump from this state to all the way to the ground state, you can't do it, because the photon dipole has only delta L equal to 1. So, the high excited states actually don't decay to the ground state in one step, it is a cascade in terms of this dipole, but then this n is large. So, if this is 100, this can be a factor of 1,000,000, and then the decay rate becomes highly suppressed compared to what is the lowest level of what you call 2 n equal to 2 to n equal to 1 hydrogen atom level, which is of nanosecond kind of time scale. Here you are going to get a huge advantage that these states don't decay that fast. Neighboring L transitions. And what is observed are the time scales. I will and this is order lifetime of such states can be of the order of a second. So, that is the game. You needed a state which lives long enough, so you can do various kind of manipulations with that, and those are these Rydberg states. And now, how you do transformations on this Rydberg state, that I will discuss next time. But this is a nice manipulation which is available, and people are actually using it quite a lot these days.